Alrighty, so which of these are exponential growth? I'm going to put letters by them just so that we can talk about them easier. So we've got A, ooh, that's trash. A, B, C, and D. Which of these are growth? C and D. So this one is, and this one is. We can tell because these bases are bigger than 1. That's what it means for it to be growth. Our base is bigger than 1. It doesn't matter that this is a fraction. It's allowed to be a fraction. It's the fact that it's bigger than 1 that lets us know that this is growth instead of decay. Okay? That's all we had to do on it. Just circle the 2. So what we're going to talk about today is we're going to take our formula from yesterday and we are going to expand it out just a single smidge. So yesterday we worked with this one here. We would talk about things doubling or tripling or quadrupling, and that would be our base. What we have on the, zooming in so you have to follow my brain. So our base was that. Our A, if you notice in what we're going to work with today, the A is still there. Our A is still going to represent our starting amount or our initial value. Our starting amount. The only thing that's really different in these two formulas here is the piece that has the exponent. And what it is it's slightly expanded outwards to show us this R piece. And what this R piece is where we can decide, or where we can use a rate that's not just double, triple, whatever. Our R is going to be any rate of growth or decay, written as a decimal. Most often, the rate will be given to you as a percent. So we're going to practice real quick. If I tell you our rate is 15%, what is that as a decimal? 0.15. It moves left 2. If I give you 3% as a decimal, what is that? 0.03. So it's really important that we remember that decimal place moves twice when we are doing percents to decimals. The last place in our formula we need to pay attention to up here is it's got both plus and minus. So when we're looking at our formula up here trying to write everything down, we're going to need to make a choice. We will use plus if we're dealing with a story that deals with growth. And we will use minus if we're dealing with a story that uses decay. And we're going to have to make the choice based on the context of the story. So we're going to look out for some key words. And we'll practice with that several times today. But it's using the same pieces. This just takes the base from over here and expands it outwards a little bit over here. So we're playing with our base is what we're playing with today. And you guys are still gonna finish writing that, Jackson. I still got some people writing. I also got some people copying off the answer keys for homework.
Isn't that what it's for?
No. It's to check your work, not to do the work for you. That don't help you at all. Don't make its way do everything for correctness. I was like, if people do that too much, I'm going to switch how I do homework. And we'll do it on the computer where you have to get it right. All right, so we're going to work with stories like this. We've got a population problem this time. So we've got here the population of a town called Albany, Kentucky is growing at a rate of 2% annually. Annually just means per year. The current population is 25,000, and what we're asked to do is to write an equation for the situation. So I'm going to write down our kind of basic form again, and what we're going to do is we're going to find the pieces and fill them in. So we're using our A1 plus or minus our r with our exponent of x. And we're going to try and find all the pieces in these two sentences to fill in what we can. So just like yesterday's, our A is our starting amount. What is our starting amount in this situation? 25,000. So we're going to start with 25,000. So the y equals, ooh, screen jumped for me. Then we're going to use our parentheses 1, and we have to make a choice here. Are we going to use the plus or are we going to use the minus?
Plus.
How do we know that?
It's growing.
It's growing. So we're going to use the plus. Then we need to put in our rate. What's our rate? 2%. How do I write that as a decimal? 0.02. 0.02 to the x. That is definitely an equation for this. I am going to simplify it before we move on. It makes it easier to make it, to type it in the calculators and stuff. So I'm actually going to simplify what's in my parentheses. We can add these two pieces together. Our 25,000, 1 plus 0.02 is 1.02 to the x. Once we do our simplification, we can use a quick double check of like what we did in the bell work to say, hey, this guy is bigger than 1. It is, in fact, doing growth, so we're in a good place. It's a great way to double check we got the sign right because it should be growing. This is going to be bigger than 1. Then what we're going to do is we're going to estimate how many people live in Albany in 20 years. What are we going to do with that 20? What are we going to do with this? Put it in for x. Exactly right. We're going to take our whole equation, that y equals 25,000 times 1.02 to the 20th power. We're substituting that 20 in for the x. And to evaluate this, we're going to use our very bestest friend. We love the calculator. And we're going to type the whole thing in just like this. 25,000 times 1.02 to the 20. So we have our 25,000 parentheses 1.02 raised to the power of 20. So we're just going to type it in just like that. Oh, we're going to talk about that. Okay, that's the next thing we talk about. So I'm going to write it down first so I don't have to switch back and forth. So my y equals 37,000, 148.68. What is this about? 37,148.6 what? People. Can we have 0.6 people? No. I'm pretty sure if you start tossing random limbs into the center of town, it will affect your population. Don't give me part of a person. Round to the nearest whole creature when it's something living. We're going to behave like humans. Okay, so we're going to round this to the nearest whole unit. So we're going to say they're going to be about 37,149 people. If we have living creatures of any kind, whether you like the creature or not, even if it's fruit flies, even if it's mosquitoes, even if it's alligators, people, do not give me decimals for people. Children still count as whole humans. You cannot give me an argument for a decibel of a person. That just means you tossed in a leg. Do not toss legs into town. It will affect your population. Okay, so living creatures, we're going to round to the whole number. For sure. Questions on this first one? This is the first one we've done with rate. We're going to practice this a couple more times. Okay, let's do the next one. Boop. All right, this is a real thing. When you buy a new car, you buy a brand new car for $23,000, its value depreciates the second you drive it off the lot at about 15% per year. So we are going to write an equation for this particular car. So again, I'm going to write kind of our basic formula down so we can play match them up. So we're going to have our A1 plus or minus R to the X. So what's our A? What's our starting amount? 23,000. That's where the price starts. Y'all are a little shooketh about that. Or 23,000, that's our starting amount. Is this going to grow or decay? Decay. This uses a really weird word here, so we're going to use the minus. It says depreciates. That is almost entirely used on vehicles. That is where you hear it most commonly. Sometimes you'll hear things talk about an investment depreciating or houses, things like that. But more often than not, it's used on cars. And it always means loses value. So depreciation is a form of loss. So that means this is going to decay. What is the rate we're using? 15%. How do we write that as a decimal? 0.15 or 0.15. I don't care if you put the 0 on it or not. To the X. So we filled in all the pieces we have for A. I'm going to simplify it before we move on to the part B. So I always want to simplify. What the simplifying does is it helps us double check that we set it up right for growth versus decay. It also saves us from typos in the calculator. So you're going to want to simplify this. We have 1 minus 0.15, which is going to give us what as this base? What's going to go in the parentheses? Yeah, 0.85, which lets us do our spot check right here. This guy is less than 1, which means it is decreasing, which means we set it up right. It gives you a spot check right in the middle there that doesn't take any extra effort. So then what we're going to do, all the words in there, is we are going to evaluate the value of the car in 5 years. So what are we going to do with that 5? That goes as our X. So we're going to have our Y equals 23,000 times 0.85 to the power of 5. And we're going to type that in the calculator. There are 23,000.85 to the 5th. And you're going to type it in just like that. You could also do 0.85. That's totally fine. It doesn't matter if you have the 0. You should wind up with the exact reason why we don't buy brand new cars. Because after 5 years, my $23,000 car is now worth barely over 10. That is a real thing. Cars devalue like that. So we have our Y equals, that was 10, 205, 20, 222. What unit are we talking in here? What is this about? Money. So how many decimal places should we have when we're talking about money? 2. Cut it off right there. So the value of our car after 5 years is $10,205.22. It is worth less than half of what it was originally worth 5 years ago. Because that's how cars are valued. The second it's driven off the lot, it starts losing value.
Why? Because of the mileage or something?
I have no idea why. But that's the way it's going. That's the way the market works. And 15% is honestly pretty good for keeping the value of a car. The more expensive the car, actually, the worse it depreciates. And that's true for almost every car. Not saying everyone. There are some, like the uber fancy sports cars, don't lose as much. And surprisingly enough, certain pickup trucks, like a 2004 Ford F-150, doesn't depreciate. It's weird. So, but this is true for most cars. But that's why you shouldn't buy a brand new car. Get a used car. Then it's already lost most of its value, and you're getting a deal. Okay? Questions on this one? Because we've done two kind of simple ones. I'm going to toss one with a wrench at you. There's one that's a little weird, so we're going to do one that's a little weird. This is our last one. Again, real thing. This is a science thing. We've got caffeine has a half-life of 5 hours. That is a phrase you'll hear in chemistry a lot, half-lives. You'll also hear this is in a pharmacology kind of way, meaning medicines. So half-lives happen a lot in chemistry, mostly with radioactive things and with medicines. So all that it means is it decreases by 50% in the weird unit of time. So we have another weird unit of time situation. So what we're going to do is we're going to start by setting up our equation most of the way, and then we'll figure out what to do with the weird unit of time. So again, I'm going to give us our kind of basic formula that A1 plus or minus R, hello dear, to the X. Here, let me have your pass, just so I remember to mark it down so I can fix your attendance. Of course. It's because if I don't have the pass, I will not remember to go and fix your attendance. It's all good. All right. So let's fill in the pieces we know. What do we know? A. What's A? A is 100. So we're starting with our 100 out front. Another 1. Is this going to grow or is this going to decay? Decay. Half-life always is a decrease. Always. So this is going to be a decay. By what rate? 50%. As a decimal. What's 50% as a decimal? Yeah, 0.50 or 0.5. We're still going to use our hour for our unit of time, but we have a weird unit of time situation. So in order to figure it out, I'm actually going to look at my part B and think about my 15 here. Because it's decaying half in every 5 hours. So we're going to look at our hours of 15 here. If we have 15 hours, how many times is it going to cut in half? 3. Because this is 5 hours, this is a chunk of 5 hours, and this is a chunk of 5 hours. So what we're really doing is we're taking our 15.
Wait, but where do you get the 15?
I was looking here as an example. I just picked one. And we're going to divide it by our 5. So if we didn't have that 15, what if it was 21? Or what if it was 2? Or something that doesn't easily divide by 5 in our head? We're going to come up here to our exponent, and we're actually going to divide by our weird unit of time. So whenever we have a weird unit of time, you're going to divide your exponent. It's not going to happen super duper tons of frequently, but it does show up. Okay, we will continue to practice it as we go. But so whenever we have a weird unit, we're counting by 5s. That's an I, but whatever. Whenever we have a weird unit, you're going to divide your exponent by that weird unit. We did one like that yesterday, but we're going to hit that several times because that's going to be one of the things that people forget most frequently. Okay? So from here, we're going to finish simplifying it. Our whole equation is our 100. We're going to simplify our parentheses. 1 minus 0.5 is 0.5 because we literally cut it in half. And then we have our exponent of x over 5. That's our equation here. That's the best equation we've got. So when we're coming down here to give an estimate of how much caffeine is left in your body 15 hours after drinking a Mountain Dew. Yes, I did look up the half-life of caffeine to write this problem. We're going to take our 15 and we're going to put it in for our x. So our y is 100 times our 0.5. And we're taking our 15 and putting it in for x. You can either type it in the calculator like this, or you can simplify and put it in the calculator. I'm going to simplify it so we can see why we care. Because our 0.5, we actually wind up with an exponent of 3. Just like we said, we had 1, 2, 3 groups of 5 hours. That's where that 3 is coming from. It's how many 5-hour chunks we've got. So what we're going to do is we're going to type this in the calculator and figure out how much caffeine is left in your body 15 hours after drinking a Mountain Dew. So we're going to go to the calculator. Burp, burp. 100 times 0.5 to the third. And we have 12.5. 12.5 milligrams. Which is why, especially if it's more than one Mountain Dew that we drink, sometimes it affects our sleep at night even if we drink it in the morning. Because you still have 12 milligrams caffeine in your body even 15 hours later. And the more caffeine you start with, the more you're going to have left over. She says while drinking her coffee. Caffeine and I are besties. Okay, so the ones with the weird unit of time, you just got to be extra careful on. Questions on this one? Hell, zombies today, just saying. Okay. That's it for tonight. So you're going to have the rest of the time, which is about 15 minutes, a little more than actually, to work on 7.1. Yesterday we could only do a very little bit of it because most of the problems had rates. So today's your day to work on them with these rates. I will put our kind of basic form back up here in case we didn't write it down because it's not written on your homework. So that's our A1 plus or minus R to the X. So I'm just going to put that there for you. If you don't have it written down, you need to. So you're going to need your computers tomorrow. So please bring your computers. We're going to practice stuff on Alex tomorrow to continue working with this stuff. Okay? So, but like I said, you guys get the rest of today to work on the homework. You guys should be able to finish 7-1. You guys have 15 minutes. So even if you didn't start it yesterday, you should be able to get there. If you got questions, let me know. Work on stuff. Ask questions. All that jazz. Work on stuff, ask questions. Nappy nappy.